In this video, I wanted to do a brief introduction to sequences and series, mainly focusing on sequences. Series really are considered the third branch of calculus, the first being derivatives, the second being integrals, and now series. And I think a frequent question about sequences and series is why? Why do we use them? Why do we need them? Because derivatives answer the question, how do we find the slope at any point on a curve, and integrals answer the question, how do we find the area under a curve. But series are a little bit trickier, and there are a lot of applications to series that nowadays we look at and say, well, we can use technology to do what series used to do. But series allow us to do a lot of analysis of functions. They also allow us to do a lot of programming. There's a lot of different applications to them when it comes to music and probability. Any kind of computer system, any kind of programming usually needs a series. It's a very logical process. For us in Calc 2, we're really focused on forming new functions and studying difficult functions. Much the same way that tangent lines allowed us to analyze curves, series will allow us to do even more. The difference between the two as a sequence is simply a pattern of numbers. We identify the pattern, we identify if the pattern converges to a certain value as the sequence or pattern gets larger. A series is a sum of the pattern. We are mostly concerned with series. In fact, the AP exam will only focus on series. And again, that is that sum of a pattern. But to understand series, we do need sequences. We need to understand the pattern before we can start finding the sum of the pattern. So let's get started with some simple sequences. So for example, I've defined 4 sequences here, the first being 1 over n squared plus 1. I'm just going to list the first 4 terms of each of them. So like this first one, if n is 1, I say, well, the first term then 1 over 1 squared plus 1 is 2. So 1 squared plus 1. The next one would be 1 over... Now, again, we started with n equals 1. Well, the next term would be n equals 2, and then n equals 3, and then n equals 4. That's all we're going to do. We're just going to keep plugging in the next n to build our sequence. So we do that, 2 squared plus 1. So this will be like that. Next we do 3 squared plus 1, so the next term would be 1/10. And finally 1 over 4 squared plus 1, 1/17. So there's our first sequence, our pattern. Next, 1 over 3 to the n. Well, 1 over 3 to the first, of course, that's just 1/3. 1 over 3 to the second is 1/9. 1 over 3 cubed is 1/27th, and 1 over 3 to the fourth is 1/81st. Okay. Now, I just want to mention that in both of these cases, as I said in the previous slide, we're always concerned with whether or not something converges. That's essentially saying, does it have a limit? And you'll notice here, in this first one, 1/2, then 1/5, then 1/10, it's getting smaller. This does converge. It converges to 0, this sequence. The pattern, as the denominator will continue to get larger and larger and larger as we plug in more numbers, while the numerator stays at 1. This will converge to 0. This next one, 1/3, 1/9, 1/27, the same thing is going to happen. This will also converge to 0. Whereas this next one, let's plug in 1, we get 1 plus 2 over 3, so we get 1. The next would be 2 plus 2 over 3, so 4/3. 3 plus 2 over 3 is 5/3. And 4 plus 2 over 3 is 2. This will not converge because the numerator will continue to grow and the denominator is locked at 3. This will diverge. This sequence will just continue to grow. Okay. Finally, I thought I'd throw one in here that's kind of interesting. You see that little -1 there? That makes this what's called an alternating sequence. I'm just going to put ALT for alternating, because when I plug in 1, -1 to the first is negative. And then I have 2 over 3 plus 1, so negative 1/2. The next time I plug in 2, well, negative 1 squared is positive. Now, normally we wouldn't put a positive, but I'm going to. And 2/5. Next, we plug in 3. Negative 1 cubed is negative. And 2/6 is 1/3. Next, 2 to the 4th is positive, so 2/7. So this is what's called an alternating sequence because some, depending on the term, it's positive or negative. Next, I want to actually find the sequence that determines the pattern. I want us to try and come up with that definition. A of n equals. Now, I guess the first thing I would look at, and you're not expected to come up with some really random, bizarre sequences. I mean, some of the ones on the previous page, like 1 over n squared plus 1, that could be kind of a hard one to see. But this one, you'll see that, the top is always multiplying by 3, and the bottom is always multiplying by 5. So I know it has to be multiplying by 3/5 every time. And I'm going to put 3/5 to the n because, of course, as we go along, we'll just multiply by 3/5 more and more times. And the first term was 1/4. So it's just that. Okay, now check it a little bit. If I plug in, and we could say, why don't, like on the previous example, the previous slide, we always started at 1, at n equals 1. So if I did that, I'd get 1/4 times 3/5. That would be 3/20. So you could, or you need to adjust that, or, I'm just going to put this, or you could specify that n is equal to 0 to start with. It really doesn't matter. I think usually we want n equals 1 in your book. We usually want to start at n equals 1, so you may need to adjust. But that's our sequence. We just figured out what was happening, and we set up a kind of an exponential equation to show that. Now this next sequence, 1/2 multiplied by negative 2, and negative 1 multiplied by negative 2, and 2, we're multiplying by negative 2 every time. So we could say, it's negative 2 to the nth because we're multiplying by it every time. We started with 1/2, and again, check it. If I plug in 1, I get the second term, so I should do this. And then I can say starting at n equals 1. So we really just are finding an equation that describes the pattern. That's all sequences are. They're patterns. Finding out what the pattern is, finding out a way to describe the pattern, finding out the terms in the pattern. That's all sequences are. Finally, the big question, as I alluded to earlier, is does a sequence or pattern converge? What this means, quite simply, is does it have a limit? And if so, what is that limit? Well, sequences go towards infinity. We plug in larger and larger, n approaches infinity. We just plug in larger and larger values. So really, like this first example, think about it this way. Is there a limit as n approaches infinity to 1 over n squared plus 1? Well, use your L'Hopital's rule, not L'Hopital, excuse me, but use your rules from pre-calc. High powers on the bottom. This will continue to grow. Therefore, the limit is 0. The sequence converges to 0. If the sequence was going to infinity, then we would say it diverged. So this second one, again, if n gets larger and larger, 2 over a really big number approaches 0. This third one, the high power's on the bottom, so the limit would be 0. Every single one of these, we're asking what happens as n approaches infinity. Okay, so like this one, limit, I'm just going to write that again, as n approaches infinity. That's what we got to think about. So this one approaches 4/6. This one, well, the limit does not exist because the high power is on the top. And this last one is 3/5. So out of all of these answers, only one of them doesn't converge. The one that has a non-existent limit. This one diverges. Okay? So the nice thing about sequences are it's just playing with patterns, and it uses the same rules for convergence that we used for limits. If we can get an answer, that means the pattern converges. If it's infinity or negative infinity, then the pattern or the sequence diverges. And whatever we say the limit is, that's what the sequence converges to, because all we're saying is we're just plugging in larger and larger values of n, just like back when we evaluated functions, we were plugging in larger and larger values of x.